Best animations of worms we've seen today. So, I'd like to invite our next speaker, Wada-san, who's here with us now, to talk about flows in display cases, a very different scale here. Thank you. Do you need to use your computer or is this?
Yeah.
One, but I think it's fine very much.
So, good morning, everyone. My name is Hiroshi Wada from the Tokyo National Museum in Japan. I am truly honored to have the opportunity to present at this international conference. I would like to express my gratitude to everyone who contributed to organizing this event. So let me introduce the Tokyo National Museum where I work. It is located in an urban area. The new museum is surrounded by a lot of greenery. Within the museum grounds, there are several buildings, each constructed in a different year. Today, my presentation will focus on the building outlined in this red on this slide called the Honkan. The Honkan itself is a historical building with a history of approximately 90 years. Even today, it serves as an exhibition space. And let me give you a brief tour of the Honkan. As you enter the building, you can see a grand staircase in front of you. After going up this staircase, you reach the first floor. You can see beautiful historical decorations. There are several galleries showcasing a wide range of Japanese artwork, paintings, statues, ceramics, and this is room 5, where Japanese armor is on display. Today's presentation focuses on the project to renovate this display case. What you see here is the display case before the renovation. In 2023, we carried out a plan to renew this old display case. The room 5 you just saw is located here on the floor plan. One of the reasons for renovating the display case is the poor environmental conditions in the Honkan. Here are visualizations the changes in relative humidity in the first floor of the Honkan throughout the year. As a historical building, resulting in unsuitable, as a historical building, the facilities are outdated. So resulting in unsuitable humidity levels in all areas. Artworks are highly sensitive to fluctuations in humidity. To protect them from drastic environmental changes, high performance display cases are essential. Typically, we use humidity control materials to stabilize the humidity inside display cases. In recent years, we have installed circulation fans in the display with the humidity control materials. Humidity control materials are made from processed silica gel. This material has both moisture absorbing and moisture releasing properties. It stabilizes the humidity inside display cases without the use of electricity, widely used in many museums. So while using humidity control materials, there was something we did not fully understand. The airflow patterns inside the display case and how humidity transmission within it. To address this, we planned an experiment to visualize and understand the environmental conditions inside the display case. The experiment was quite simple. First, we created a mock-up with the same shape as the planned display case. Various sensors were then installed in the mock-up to measure temperature, humidity, and wind speed. Here are the specifications of the sensors we used. Inside the display case, we placed 9 ports attaching sensors to each of them. The display case has an internal volume of 3.56 cubic meters. Sensors were placed in various locations, as you see. This is the humidity control tray where humidity control materials are placed. Its location is indicated by the yellow highlighted area. The fans were installed for air circulation. It is positioned at the center of the bottom here. Airflow by the fan enters the humidity control tray, and then air is released into the interior of the display case through the airflow slit created on the side. In the experiment, the width of this slit was designed to be adjustable to 3 different levels. First, this visualization shows how the number of operating fans and the slit width affect airflow. The data for this diagram was generated using wind speed sensor. Readings from the 3 poles indicate in top and right figures. Next, we increased the density of wind speed sensor poles for more detailed monitoring. Therefore, we could only visualize half of the display case interior, but this allowed us to capture finer airflow patterns. Here is the wind speed distribution when the slit width is 15 millimeters. Similarly, here are the visualizations of the wind speed distribution when the slit width is 10 millimeter and 5 millimeters. By visualizing the wind speed distribution, we confirm that airflow reaches the upper section of the display case even with a slit width of 50 millimeters. Additionally, since significant wind speeds were not observed in the central area of the table where artifacts will be displayed, we determined that under these conditions, the impact on the artifacts would be minimal. So in Japan, it is generally required to maintain a relative humidity of 55% for many artifacts. This is a standard value. If the humidity exceeds this standard, moisture absorption is necessary, while lower humidity requires moisture release. To investigate these phenomena, we created artificially high and low humidity environments and conducted experiments. Humidity control materials are designed for specific target humidity levels. Users purchase the materials corresponding to their desired humidity level. In this experiment, we bought and used humidity control materials for 55% humidity. Here are the visualized results of environmental changes from a dry state. The slit width was fixed at 15 millimeters, while we compared the cases where 1 fan and 3 fans were operating. From left to right, it shows the changes in temperature, relative humidity, and absolute humidity simultaneously. In both experiments, the target humidity of 55% was not reached, but the experiments were conducted once the humidity stabilized. Next, here are the visualized results of environmental changes when from a wet state. Similarly, the target humidity of 55% was not reached in this experiment, but we confirmed that the moisture absorption function was effectively working. What we wanted to understand was the relationship between the number of operating fans and the time required to complete humidity adjustment. To calculate this time systematically, we used changes in absolute humidity. First, we calculated the moving average of the absolute humidity values and then differentiated the resulting curve. Since the differentiated results still contained a significant noise, we applied a second moving average to smoothing the data. Finally, we defined the time at which the slope of the resulting curve stabilized at 0 as the time when humidity adjustment was complete. As a result, when humidifying with humidity control materials, it took approximately 7.5 hours with 1 fan and about 8 hours with 3 fans. On the other hand, when dehumidifying, it took approximately 13.5 hours with 1 fan and about 14 hours with 3 fans. Therefore, under the conditions of this experiment, the number of fans did not significantly impact the humidity adjustment time. A single fan is sufficient for humidity control under normal conditions. However, there may be situations requiring emergency responses during exhibitions. As a result, we decided to install 3 fans in the display case, allowing the number of operating fans to be adjustable. Based on this design, production of the display case began at the factory. Here is the new display case. I believe we were able to create a very beautiful display case. This is the temperature and humidity change data. You can see that the humidity is very stable. Upper figure shows the blue line shows the relative humidity change. The data on the disturbed humidity, for example here, is due to the opening of the display case to change the exhibit. Here are the conclusions. No correlation was observed between the humidity adjustment time of the control materials and airflow speed. Even with 1 fan and a slit width of 50 millimeters, humidity can be evenly transmitted throughout the display case. A comparison with cases without fans still needs further investigation. For effective humidity control, increased contact between unconditioned air and the material is essential. This suggests that optimizing the way air flows toward the control material is critical. This is an important consideration for future display case designs. Here is the acknowledgement. I would like to express my gratitude to everyone involved in the production of the display cases, including Kopio Company and Kyushu Keisoki Company. Thank you for your attention.
Thank you very much. Very culturally important work. Are there some questions about that? At the back, sorry.
So I was wondering what kind of material did they use to remove moisture?
Moisture?
What material do you use?
That is a processed silica gel.
Okay.
So,
Silicon gel based.
Silica gel based, humidity control material.
And it's like a porous medium where you blow your air through. Or
That's right.
Yeah.
Sorry, there was a question at the front.
Is the air exchanged or recycling?
Almost all of the air was recycling in this showcase. So because the air exchange rate in the showcase is very low.
So I hear sometimes the gas emission is very important.
That's right. So I said the emergency response is need is sometimes we catch the high concentrate of the volatile organic compounds from the not artifacts from the pedestal or the inside the plywood and painting materials and so
To
on.
keep the low concentration level.
Yeah. Thank you.
Okay. I just have a question. How you at the end you gave some times for 8 hours or 14 hours to achieve the desired humidity. How important is it that time? Because presumably these are on display for months or years. If it's 8 hours or it's 12 hours, does that make a difference?
I don't think so huge problems in 8 hours, 40 hours, but some kinds of the special artifacts with made from the special material. It is very sensitive, the fluctuation of the humidity. So in that special case study, we must minimize the treatment time.
Thank you very much. Let's thank the speaker again. I'd like to invite Y, also from the University of Melbourne, to come to talk to us about some self-assembly. About